All right, welcome everyone to the CS elevator pitches of the Polygent Symposium. It's our 7th Symposium of Rising Scholars. We're so happy to have you here. So my name is Daniel Whitaker. I'll be moderating the session today. And obviously the goal of this is to celebrate your hard work. You know, all the work that you put into your projects. We want to be able to celebrate that with you, learn a little bit about what you studied and certainly ask some questions on, you know, what you plan to do after you move on from this project, you know, how you're going to be able to transition into the future. So we have 5 students that will be presenting today on a variety of topics. And then there also will be a fellow member of the Polygent's team that will be scoring each student's presentation, which will help us determine prize winners after the event. So if you have questions, you can actually type them into the Q&A there at the bottom. What we will do is ask questions, a few questions after each presentation, and then we'll move on to the next one. So again, everybody, welcome. Our speakers today and our presenters are going to be Alexander Hume, who will be going first, and then I'll introduce the others as we go through it. Just a reminder, everyone will have their camera off, and then I'll turn my camera back on when you have 1 minute remaining. And other than that, I think that we are all set. So Alexander, you have the floor.
Hello, my name is Alex, and my project is using machine learning to predict systemic crises in African countries. My mentor was Nick. So first of all, what is a systemic crisis? A systemic crisis is a systematic disruption in the financial system of a country that has extreme negative effects on the economy of the country. This can lead to negative effects such as inequality, lack of clean water, and famine, especially in third world countries such as those in Africa. There are a number of key indicators that indicate systemic crises. These include inflation, domestic debt defaults, sovereign debt defaults, banking crises, and currency crises. Using machine learning, we can predict systemic crises by training on key indicator data. This allows us to mitigate their effects or prevent them altogether. So in order to do this, I first acquired a data set from Kaggle, which included features linked to systemic crises, including inflation, debt defaults, and exchange rate for USD. This data included 1,059 rows of data from 1860 to 2014. After acquiring the data, I needed to clean the data in order to get it ready for machine learning models. To do this, I first dropped unnecessary columns such as country and country code. And then I standardized the values of some columns based on their mean and STD to calculate their z-score. So as you can see in this picture here, exchange rate to USD and inflation will get standardized so that they are scaled the same in the machine learning model. After cleaning the data, there were a total of 10 features, which are not all shown here, which will be used with machine learning models. After cleaning the data, I split it up into a test set and a training set after shuffling it. So as you can see here, 80% of the data goes to the training set and 20% of it goes to the test set. And this is done so that the machine learning models can be trained on the training set and then tested on the test set to make sure they can generalize well to unseen data. I trained 3 different machine learning models on the training set using sklearn. The first was decision trees, the second was random forest, and the third was logistic regression. Decision trees are a machine learning model that uses a tree to make decisions based on your features in order to classify data. Random forest is a machine learning model that uses a lot of different decision trees and finds an average of the results. Logistic regression is a model that trains a sigmoid function to the model to split it up and classify data. After using these models, I used grid search CV to perform exhaustive hyperparameter tuning with 5-fold cross-validation. And this was done because each machine learning model has hyperparameters that control their performance, and taking advantage of this hyperparameter tuning with grid search CV allows me to find the best possible hyperparameters and make sure that they don't overfit to the data by using 5-fold cross-validation. After training these models, I calculated the results using true positives, true negatives, false negatives, and false positives. So this is a confusion matrix, which contains all of this data. This one is the one for decision trees. As you can see, there's true positives in the top left, true negatives in the bottom right, false negatives in the top right, and false positives in the bottom left. So based on these, 4 metrics can be calculated: accuracy, recall, precision, and F1 score, which determine how well the model performed. So these are the confusion matrices for all 3 models that I trained on the data. And as you can see, random forest had the best accuracy, recall, precision, and F1 score, making them the best model for determining systemic crises. So the next steps for this project would be to utilize more relevant features and data from other countries in order to improve training and more accurately predict systemic crises from all over the world instead of just Africa. Thank you for listening to my presentation.
Thank you. Thank you. Let me get, go ahead and for the audience, if you have questions, you can post those in the Q&A. But my first question to you, Alexander, is what made you interested in this topic? I mean, obviously you did a great job on the data set and the accumulation of, the information, but what made you pick that subject?
Well, I actually became interested in machine learning before this subject in particular. So like I wanted to try to train a machine learning model on some kind of data. So like I went searching on Kaggle for a data set that would be cool to search to train it on, and I came across this one. And I thought, like, how cool would it be to be able to predict something on as big of a scale as systemic crises using machine learning? So that's why I decided on this topic. Wow,
that's great. And then Shannon Powers asked a question: why did you choose that model?
Oh, the 3 models that I chose decision trees because they are generally pretty good with classification. And well, it's like kind of like a start to like other models. And I chose random forest because, well, I read, like, my mentor led me to read this research paper that random forests perform among the best out of all like classification algorithms out there. And I chose logistic regression because it's a really popular model for classification. And I think it was pretty interesting.
That's wonderful. And what are your plans now moving forward after you did this project? Did you learn anything that you want to take with you as you move on?
Yeah, I learned that machine learning is capable of doing a lot more, like has many more applications than I thought it would. So moving forward, if possible, I actually want to try to like find more data for this project, and then try to make it be able to like predict crises in globally. And also I want to like be able to do other projects using these models and other models that I will learn in the future.
Have you seen models like this that have actually accurately predicted a particular crisis?
Like outside of this project?
Outside of what you've done, like, I mean, is this something that's kind of new to you, or is this something that people are doing right now to try and predict these things?
Well, I'm not, at least like I haven't really looked into like if other people are doing similar.
Yeah.
But like to my knowledge, yeah, I haven't really seen it.
Yeah. Well, that's incredible. I love it. I love it, Alexander. Thank you so much. And very well done. Very nice presentation. If there's any other questions, go ahead and put them in here. Otherwise, I'm going to remove Alexander as the speaker now. And we'll actually then start to move on to our next presenter, that is Bhavik. Bhavik, are you ready?
Yeah.
Wonderful. Then I will give you the floor. And go ahead whenever you're ready.
Hi, my name is Bhavik Singhal, and I'm going to be presenting my research on MOFs. I'll be going over what a MOF is, the methods I use, and the results. Firstly, a metal organic framework, or a MOF, is a hybrid crystalline porous material dwelling with metal ions and surrounded by organic linker material. The metal ions and linker material work together to create a cage-like structure, which defines a MOF. MOFs are used for gas storage, separation, imaging, and also adsorption. A real-life example is that they provide oxygen for people with oxygen masks, and they're also important for climate change. What I focused on in my research was the most important descriptors that make up a MOF and what the most important MOF actually is. After finding a MOF dataset online, I looked over the data, fixed any null values, and reduced any columns I did not need. I ran many feature selection models. This was the main part of my project. And I ran these feature selection models on the MOF dataset. The ones I ran include correlation, mutual information, univariate, and Pearson models. I'm going to go more in depth of what each of these four are. So the correlation feature selection model measures how two variables are acting with each other. As linear scores are typically between -1 and 1, we are mainly concerned with how connected variables are, so we take the absolute value. This means the higher the correlation value, the more the two variables correlate with each other, and thus making it a more important variable for predicting the target. The mutual information model measures the reduction in uncertainty of one variable given another variable. It takes into account the entropy of each variable, which is the difference in probabilities. The higher the mutual information score, the better correlation there is between the target variable and the descriptor. Univariate selection depends on the ANOVA F value method, combined with select k-best by using the F classification method and outputting the most descriptors. Select k-best allows us to determine how many of the top variables we really want. The Pearson model is derived from the correlation model, so it contains many similarities with it. It also uses the ANOVA F measure. However, it depends on the F regression method and prints out the most important features. The graphs here show the data for the correlation and mutual information. And I also listed some descriptors for the univariate and Pearson models that were found as most important. From these results, the most important trend was how most models found that heat adsorption at different pressures and temperatures to be the most important descriptor. This means that scientists, when conducting and creating MOFs, should really focus on the heat adsorption values of the MOF and to get the greatest efficiency. Other important descriptors individual models outputted include surface area, temperature swing, and vacuum swing. Next, I also ran some models to predict the efficiency of MOFs. I ran the LARS method, known as the least angle regression model. This model is a step up from a basic linear regression model. It takes the linear regression and adds a penalty, so the large coefficients of the model become smaller. Large coefficients can cause a model to become unstable, and especially with the size of my dataset, this issue is prevalent, so it's important to utilize this penalty to reduce these coefficient values. The MLP model, or multi-layered perception model, splits your data into a train and test and ultimately has 3 layers, which run through your data and predict the outcome variable. After running the LARS and MLP to find good descriptor values, I got an average of 130 moles per ATM for the LARS method, which is a measure of a Henry's constant, and it's a sign of high efficiency of MOFs. This ran better than the MLP, which means that I should be using the LARS method over the MLP to predict the efficiency of MOFs. One key thing to notice is that this project is still going. I am currently developing a neural network that will further expand my goal to predict MOF efficiency. Right now, the LARS and MLP models will touch the surface in the efficiency part, but the neural network I am currently in the middle of developing will go even further into deciding which MOFs are the most efficient and how to find these most efficient MOFs. The results from these models pose some important takeaways. Scientists should focus on the most important descriptors when creating MOFs, especially heat adsorption values and surface area. It is also important to find the best values of each descriptor when considering the efficiency of a MOF. Thank you.
Wonderful, Bhavik. Thank you. Thank you. And again, you can post your questions in the Q&A section. Shannon asks, what part of the project did you find most challenging when deciding to do the project?
So my project kind of contains 2 main points, as I said, the feature selection and also like predicting the most efficient MOF. And as I said, currently, like I'm still trying to develop the neural network, because that's really been like an issue for me. Like I have a neural network right now, but I'm getting very high RME or RMSE values, which means that it's not a good model to run. So right now I'm trying to bring that value down and to get like a really good working neural network to predict the most efficient MOF.
That's wonderful. And what do you think how did the mentor help you the most throughout the project? What did you find most valuable?
So for me, I wanted to do a chemistry project leading into this because I really enjoyed my chemistry class in school, and I wanted to combine my interest with chemistry and data science. I was originally actually going to do something related to catalysts, but then my mentor, who is like a specialty in like biochem, she recommended me like the metal organic framework project, the MOFs, and I got really interested after watching a couple of videos of like how they work and all. So she really helped me like inspire this idea, and she also like helped me find different models to run with, because it was like my beginning of data science this year. So she really helped me find these models and like helped me run these models as well.
And you mentioned that the most important thing is the efficiencies of the MOF. So when she introduced the topic to you, was that kind of the question, is how do you increase the efficiency of the MOFs? That was the original question?
Yeah. MOF efficiency is really important because it's like scientists use this for like real life matters, like as I said about with oxygen mass, and the more efficient your MOF is, the better it's going to work. So.
Yeah, I love that. That's great work. Any more questions from the group? All right, Bhavik, thank you so much. And what we'll do now is we'll move into Dhruva will be next. And Dhruva Paul will be presenting. Dhruva, go ahead and take your camera, put your camera and your speaker on. And then what I'll do is I'll give you the floor here. And again, remember, if you have any questions, put them in the Q&A. But thank you so much, Bhavik. So Dhruva, I'll give you the floor.
Thank you. So hello, my name is Dhruva Paul, and today I'm going to be talking about my project on stock prediction. In order to get more precise predictions, I decided to focus on only one company for this project, Apple, and we'll be using a wide range of data from stock prices to financials to cost of materials, each field with 5 years worth of entries. To be precise, my project involves a neural network that, when fed certain data fields that will be explained later, will output tomorrow's Apple stock price. Although other stock prediction models do exist, most focus on the market as a whole or large indexes like the NASDAQ. They also exclusively use candlestick patterns from data on stock prices alone. The few models that do differ use certain financial data metrics, yet these still differ from the ones that I chose for this project. So let's talk about the data fields I use. The data I chose for my project came from 3 major fields: financials, stocks, and materials. In the financials field, I use the revenue, gross profit, profit margin, and return on equity. As you can see from this graph, revenue is closely correlated with the Apple stock price and is one of the most influential indicators of stock price. In the stocks field, I use the NASDAQ, Netflix, Amazon, and of course, Apple stock fields. I use the NASDAQ as it is an indicator of the general trends in stocks, and I use the Netflix and Amazon along with the Apple because they're the major players in the NASDAQ and can be used to paint a clearer picture of stock trends. In the materials field, I use the global cost of copper, aluminum, and iron, the materials of iPhones, Apple's most popular product. In fact, copper and aluminum make up 1/3 of the phones by mass. However, since each of these fields are released on different periods, with some being posted daily, some posted monthly, and some posted quarterly, I had to use an interpolation method that would fill in the gaps of unknown data. So using known data points, the method would fill in the likely pattern between each point, producing many more data entries that could be fed to the machine learning model. So the model itself, the final model that I used was an artificial neural network with 3 layers, each with 256 nodes, normal kernel initializer, which randomly chooses starting values for weights and biases, using the normal distribution, tanh activation, and L2 kernel regularization, which basically combats overfitting and underfitting. I had experimented with other models such as the AutoArima and the long short-term memory models, which treat Apple stock data as a time series. These models would try to predict future Apple stock price based solely on previous Apple stock price. However, these models performed poorly because Apple stock price fluctuates much more rapidly in recent years than in the past. The final root mean squared error of the model was about 3 to 4. That means that on average, the predicted stock prices were about $3 to $4 off from the real stock price. Since the Apple stock price at the time the model was finished was about $160, the accuracy of the model in percentage is about 97 to 98%. As for next steps, with an accuracy of 97 to 98%, the model was quite successful. In the future, this model can be adapted to include the predictions of other companies as well. This future model would be ideal for beginners to trading, as it would advise them on which trades would provide them with the largest payoff. Thank you.
Thank you. Thank you so much. Well done. Go ahead and again, put your questions in the Q&A. My question is, did you have an interest in trading yourself? Is that why you selected this project, or what got you interested in this type of project?
Yeah, actually, for like the year before, I was interested in trading. I'm trading on my own. I tried to look at the candlestick patterns, try to do it on my own, but I realized I wanted to incorporate this with data science, see if I could make it more accurate.
Have you been able to take your model and actually run it on any other stocks to see if you also had the 97 to 98% accuracy?
I have not actually, because this model was really specific to Apple itself, because I used Apple specific data. In the future, I could take other data from other companies and then try to incorporate it to maybe the entire NASDAQ as a whole.
I like it. And what do you hope comes from the data? Like, what output are you hoping for?
I'm hoping for daily changes in stock price and obviously more accurate readings. So right now I had readings that were on average about $3 to $4 off, but usually that $3 to $4 is really influential in the stock market. So I want to bring that as low as possible.
That's great. And there's another question here. Were you able to relate the cost of the metals to the Apple stock price, and what was the relationship?
Yeah, actually. So for some metals, I think it was copper in particular. Copper was really influential in Apple stock price. Others, maybe not. I think iron didn't really affect it much, but copper was definitely an influential metal in Apple stock price.
I like it. Well done, Drew. I like it. Can you go ahead and stop sharing that screen?
Yeah.
And super job. And we'll now move on to, I think it's Antonio. We have Antonio Cuan. He'll be presenting as well. And so we'll give the floor to you, Antonio. And good luck.
All right, thank you. Okay. Hi, my name is Antonio. For my Polygens research project, I created a music recommendation system using machine learning. Have you ever wondered how services like Spotify recommend you songs? It seems like magic. You put songs in a playlist and recommendations appear. My research explores possible ways to create a music recommendation system. To start, I will show a quick demo of my music recommendation program that I made during the Polygens program. So this is a web application that takes in a Spotify song URL, which you can get a song URL from the Spotify website like so. You can paste it in the bar and click the button, and the program will identify the song you put in and then show recommendations, which you can open in Spotify. This seems like a relatively simple program on the surface, but there's a lot going on under the hood. So how does this work? First, I created a data set, as data sets are essential for machine learning. Spotify actually makes data about their songs publicly available via their developer API, which I use to acquire data. I created my own data set with over 1,600 songs, and each song in my data set has audio features which are boxed in red in this image of the first few songs in my data set. These features are provided by Spotify, and they are numerical values that describe each song in some way, such as danceability or energy. My algorithms use these audio features in their computations for recommending songs. The algorithm that my web app uses is called Euclidean distance in multiple dimensions. The basic definition of Euclidean distance is that it's just the shortest distance between 2 points. But in this case, the algorithm uses the numerical features of songs to compute a distance between them. And there are multiple dimensions for the multiple song features. So there's more than 2, that's why it's called multiple dimensions. How my program uses Euclidean distance is that it first computes the distance between the liked song and every other song in the data set. Then it returns the songs with the smallest distance, which are the recommended songs. The graph depicts all songs in the data set projected onto a 2D plane. The red dot represents the liked song and the orange dots represent the recommended songs. The orange dots are close to the red dot in the graph, showing that the songs are close in terms of their Euclidean distance and thus have similar audio features. Intuitively, we should perceive songs with similar audio features to be similar, which is why I chose to use this algorithm because it is closest to our intuitive understanding of how songs are similar to each other. Another algorithm I explored in my research was k-means clustering, which essentially computes clusters of similar songs together based on their audio features. After clustering, a recommendation system would sample songs from the same cluster of the like song and return them as recommended songs. The graph shows the clusters of songs my algorithm generates when the songs are projected onto a 2D plane. The k-means clustering method is better for exploring in song recommendations as opposed to the Euclidean distance method, which is better for strictly identifying the most similar songs. In conclusion, my work explores possible approaches for music recommendation. A central part of how my recommendation system works is that the machine learning algorithms look at the audio features of songs and recommend songs that have a small Euclidean distance to the given like song. In the future, I could test the music recommendation program with people to evaluate the quality of the song recommendations in real life. For example, I could host my music recommendation system on a website where users are able to give ratings on the quality of recommendations. I enjoyed working on this project, and I'm happy to be able to share my work. Thank you.
Thank you, Antonio. All right. Let's hear some questions here. All right. How is your recommendation system different from others that exist? Like what would be different from like Spotify or Pandora?
Yeah, so with these large music services, they have a lot of data on all the different users, like user-specific data. But my work is more of with a limited set of data. You know, I don't have access to, you know, all the users on Spotify and what songs they listen to and so forth. So I sort of explore an approach to music recommendation with more limited data, like just based on the features of the songs themselves rather than other users.
Thank you. And then Shannon's asked, why did you, well, this is it's got a few parts to it. So first, why did you choose to do this project?
I have a background in music. I've been playing piano for many years. And so I wanted to sort of merge that interest with my passion for computer science and machine learning.
Did you want to mimic an algorithm like Spotify, or was there something missing that you wanted to add?
I didn't want to mimic it exactly, but I was sort of inspired by it. And like I said before, you know, I sort of want to explore how one could recommend songs without all this extensive data on users that these big services have. So that's sort of the approach I took to it. I took to my project.
And one more question for you. I mean, when you worked with your mentor, you really enjoyed working on the project. What was the one thing that you felt like really helped you see the project through that the mentor helped you with?
Actually, at first, my mentor really helped me kind of get an idea for my project and also where to start. At first, I had a different idea, but after working with a mentor, we picked this music recommendation, which I think was a good choice. And mentor also helped me point me in the right direction. I wasn't sure where to start for this project, and he helped me point to like getting data from Spotify. That really helps.
And were you familiar with the methods already, the cluster method and the Euclidean method?
K-means clustering, I was familiar, but Euclidean not as much. So yes, that's another thing my mentor helped me with was choosing the algorithms.
Well, that's great. Thank you so much, Antonio. You can unshare your screen. Our next presenter will be Tejas Oberoi. So Tejas, if you want to go ahead and share your screen, and I will give you the floor.
All right. Hello, everybody. Can you guys see my screen?
We can.
All
Yes.
right. So I'll start. Hello, everyone. My name is Tejas, and my project is on evaluating baseball pitcher efficacy using machine learning. So as a part of my high school varsity team, we saw some erratic ups and downs, including some heartbreaking losses in the last inning. Therefore, I thought of exploring this unique research topic to make practical conclusions involving physical features of a pitcher to help my team become better for the upcoming season and to help scouts evaluate future talent. As a part of my analysis, I only considered pitchers with more than 1,000 pitches and used the 16 features in the table as shown over here as inputs for my models. And specifically these 16 features out of the 80+ StatCast features because they're physical features, meaning you can measure them using sensors or through your eye. So it does not rely on an in-game event, meaning that scouts can use these features without seeing a pitcher in a real game. You can just see the pitcher pitch on the side. So these would be very helpful for scouts. And then for each pitcher, I computed numerical values for each feature by combining the pitch by pitch data provided by StatCast using percentiles, relative frequencies, or information entropies, depending on if the variables were categorical or quantitative. And then also this also made the project really tricky and unique because no other papers and projects involving sabermetrics I saw use these features. A lot of people tried to use in-game features because in-game features tend to help in predictions, but without the in-game features, the predictions become much trickier. So what I'm trying to predict is the WHIP, which is a pitcher efficacy metric that aims to compute how good a pitcher has been. So the lower, the better. So I use neural networks and linear regressions. And then I use the neural network because if you have enough data and you're in ideal scenarios, a neural network is theoretically, it can solve almost any problem, theoretically, if you again have enough data. And then I use the linear regression because as you can see from as I'll explain, I wanted to do even more analysis. So for the neural networks, I tried to predict the actual value of the WHIP for each pitcher. And I've shown in these graphs the the validation accuracy. The validation accuracy was about 57%, which was not very high. So therefore, to gain further insights into evaluating this WHIP metric, I also created linear regression models for each feature because I decided to do some feature analysis to try to explain why the neural network was not able to find enough patterns. And as you can see in this slide, these are all the linear regression analysis graphs of all the features versus the WHIP. And as you can see from the results, the ball frequency feature outlined in the red graph here seems to show the most correlation among all the other features. Most of these other features, as you can see on the top, they barely have any correlation based on these scatter plots. So therefore, in the ball frequency linear regression model, the root mean square error was less than in the neural network because the neural network had more features that resulted in more noise in the data. And in addition, it is possible that the neural network treated the problem like a linear regression based on the similar accuracies recorded, like 53 to 57%, 56.7%. So they were very similar, implying that the other features were not helpful in improving neural network model performance. And then as shown in the table to the right, the ball frequency versus WHIP was the only regression graph with a statistically significant correlation based on p-value less than 0.05, which means that the root mean square error was significantly less than the standard deviation of the whips. And that was only for the ball frequency feature. All the other features, as you can tell, their p-values are way higher than 0.05. So which means that there was no significant correlation. And this is surprising because many people think that features like ball velocity and off-speed pitch frequency, which are thought to be pivotal indicators to determine good pitchers in MLB, like they might not be as important because there was no correlation between them and the whip. So therefore, based on the low p-value and the linear regression graph, for the whip metric, the frequency of balls thrown is the most important feature. So this is very important for scouts and recruiters because they can use these results from these physical features to evaluate a future pitcher's success instead of just relying on cliche beliefs like, oh, this pitcher can throw 100 miles per hour. They're going to 100% be successful. They're going to be the best pitcher ever, because that's not necessarily the case. Like throwing strikes, which means having a low ball frequency, is very important. So I'm also, and then in addition, since I only use physical features, these scouts, like they don't have to look at, as I repeated earlier, they don't have to look at a pitcher in an in-game scenario, since all the features can be just measured using their high-tech sensors. And I'm also wondering whether the results will be different for high school or collegiate level, where the pitchers are maybe more predictable and the speeds are not as erratic, resulting in potentially less noise in the data. Therefore, I plan to continue improving my results by running more models with more types of features and output metrics. For example, I'm already running similar models on more output metrics, such as like other pitcher efficacy metrics, which have different formulas, but they try to measure how good a pitcher is, because the current feature pool and data size isn't enough. But for now, I'm using my current statistical results to emphasize to my team that throwing strikes is more important than throwing hard. And trust me, at the high school level, almost everybody thinks throwing hard is most important. Like everybody wants to throw 90 miles per hour. Everybody wants to just throw very hard. But throwing strikes, having a low ball frequency is more important. Thank you.
Thank you, Tejas. That was great. I have a question for you. So you had said, hey, the old cliche, throw the hardest, and that the high school players, they like to throw hard. But what is baseball standard right now? Like, I mean, what you're arguing makes sense, that a low ball frequency is, you know, a very good determiner on how well a pitcher can pitch. But when you're thinking of scouts that do it now, do you know what their main areas of focus are?
Yeah, so since my data is from the MLB level, at least for the MLB level, almost every pitcher can throw like at least in the high 80s. Like most of them throw in the 90s, and some can even throw in the hundreds, as I said. But like in the MLB, since like almost any hitter can hit any pitcher, so maybe that's why also the speed is not too significant. And what matters is throwing accurately at certain spots so that the hitter gets fooled. So these scouts, they're like, so they're looking for not only speed, they're looking for not only accuracy, they're looking for accuracy at specific spots. Like if they can throw in the upper right when they need to, if they can throw in the lower left when they need to, and so forth.
Gotcha. Do you pitch yourself?
Yeah, I do. I don't throw very hard.
Well, do you throw strikes?
Yeah.
Okay, good. And Shannon asks, obviously a cool project that you're tackling a real world problem for you, right? It's a real world thing that you're experiencing. That's great. If you could add anything to the model, what would you add?
So right now so what I'm trying to do is, like, for the other output metrics, I'm trying to even add whip as a feature, and that would hopefully help the model improve its accuracy. I haven't done that yet, but because, as I said, since the current feature pool does not provide enough patterns for the model to try to figure out, maybe if you add output metrics, like since I'm doing another output metric, if you add whip to the feature pool in the input feature pool, then maybe they'll help the model become better. Because as I said, previous papers, they all use much different features, like in-game, like how many strikes there are, how many balls there are, how many outs there are, because that heavily influences these types of events. But I tried to avoid that just to help scouts and recruiters, because they care about the physical features.
Right. No, that makes sense. That's wonderful. Thank you, Tejas. You're all set. If you can unshare your screen. We did have one speaker join and had difficulty getting into the practice session. So I'm so sorry I didn't get to introduce myself, but I think it is And I'm so sorry. I want to make sure I get your name right. So I'll let you pronounce, I'll let you introduce yourself. Is it Mihir? Mihir?
Yeah, that's right.
I got it right. Okay,
Yeah.
perfect. Well, sorry that we couldn't get you into that practice room, but I'm going to give you the floor. And now the floor is yours.
Thank you.
You're working to share your screen?
Yeah, it's not
Yeah, no
allowing
problem.
me to.
No problem. We'll take a minute here. Let's see. Hold on a sec. We have a little tech doc here. Let's see if I need to change anything for you. Let's see. Let me try this. If I make you the host, let's see if you can share the screen. Or do you got it?
I think it might be something on my end. It's not
Okay.
showing me which screen is which.
Oh, gotcha. Go ahead. Take your time.
I think this should work.
Well, we have a lot of professional CS students in here, so anyone wants to drop tips in the Q&A, share it with us.
I think it may require it's something else which I might have to fix later, but I can present mine without sharing my screen.
Okay, no problem. Then I will give you the floor.
Sure. Hello, everybody. My name is Mihir Srivastava, and my project was about researching the impact of Moore's Law on progress and innovation in the chip-making industry. I'll be sharing a brief overview of what I found. In the 1970s, Moore's Law, which was Gordon Moore's observation that the number of transistors per computer chip was doubling roughly every 2 years, emerged due to the technological and economic conditions of the time. Over time, Moore's Law evolved to have a more general meaning of a constant increase in processor performance. Moore's Law's rise led to the microprocessor industry focusing on solely increasing transistor count and reducing transistor size, which was both the easiest and the cheapest way to increase performance at the time. Today, however, Moore's Law is starting to stagnate for a variety of technological and economic reasons, ranging from the physical limitations on how small transistors can get and how much heat they put out in a microscopic area, to exponentially increasing prices for chip-making technologies. These barriers are contributing to other aspects of microprocessor design, which had stagnated when Moore's Law first arose, to come back and drive the industry forward, such as different instruction set architectures and different computing models. Chip makers are increasingly switching to developing more and more on these attributes of microprocessor design, and it is increasingly becoming clear that the future will have a lot more diversity in terms of different types of chip design and type as well. For example, heterogeneous compute has led to the development of various co-processors for specific tasks, whether it be machine learning, crypto mining, graphics rendering, or image signal processing. Another recent development has been that of heterogeneous core types, which has a processor have separate performance and efficiency core types. This leads to increased efficiency when doing simpler tasks, and greater performance and less power draw when more performance is required. Such developments have been the source of many performance improvements in recent years, and it is these types of developments which will continue to drive the industry forward as well. Moore's Law got us to where we are today, but as the industry starts to shift its focus away from it, we will enter a new era of microprocessor design with much more competition, diversity, and choice, all of which are only good for the industry. Thank you for listening.
Thank you so much. And when you think about the evolution of the technology and moving away from Moore's Law, Did you find anything in your research that kind of gave you a new kind of rule kind of that you would follow, or a new kind of the new guiding principle per se?
Well, that was something that I did consider and look for, but as of now, it seems that the industry, it's very diverse in terms of what improvements are going on. So there isn't any standard rule now. In a way, it's sort of back to pre-Moore's law when there was a lot of diversity and choice, and there wasn't really that one thing which the industry was focusing on. So as of now, there isn't, but my prediction is that there will be some new law for some new type of improvement in the next 5 to 10 years.
That's great. And we have a question here from Jordan. Obviously, she's saying this is an interesting topic, and it certainly is. How did you decide on this topic, and where did the passion for this topic stem from?
Sure. So I've always been interested in why the software side of things for computers, that's been progressing very rapidly, especially over the past decade or so. However, for like the hardware aspect, I had noticed that there wasn't that much improvement. And for a span of about 5 to 7 years in the mid 2010s, there was barely any improvement at all. And noticing that, I was just wondering why it was that hardware wasn't changing, but the software was. And that's sort of what got me interested in finding out how the industry had come to this point and what could be done to perhaps fix it or drive it forward.
That's wonderful. And when you think about working with the mentor, what was it that the mentor helped you with most throughout this project?
My mentor, he helped me with understanding more of the intricacies of the specific industries. My research primarily focused on like the heavy computing industry and the IT industry. So for their needs, he helped me understand what exactly it was that they needed and how exactly the chip making industry has sort of shifted to adapt to their needs. So my mentor helped me with that, and also understanding some more of the progress as he was there when a lot of the improvements were happening.
I love it. I love it. All right, looks like we have maybe a couple more here. All right, if everyone can turn their screens on, and we'll kind of go do a little wrap up here. So this goes for each of you, and we'll kind of go in the order that we presented in. What part of the learning and conducting research surprised you? So Alexander, you go first.
Well, going into it, I kind of thought that machine learning was all about like learning about the models themselves and like learning about like have the technical stuff. Like last summer I took a course on machine learning. There's a lot of learning about like how neural networks actually work, like forward propagation, back propagation, and everything. And I realized that that's not as important anymore because people have already done all of that. And it's more important to understand how to use them in order to apply them to a lot of applications. So that's like something I learned that I think was really interesting.
I like that. Thank you. What about you, Bhavik? What surprised you the most?
For me, like I was really surprised of how wide or how like the big the scope is for computers or for data science machine learning, at least for my topic, MOFs. I didn't know anything about it going into it. So I was assuming it's like a niche topic. It's a very small topic. I was researching many papers. I saw like at least like 500 to 600 different papers on different aspects of MOFs. So that kind of surprised me. It's like you can go in many different directions and there's still probably going to be 500, 600 more a year later, right? Because there's so many different kinds of like topics you can cover in one, I guess, unit, or like for MOFs especially, there's so many things you can cover. So that really surprised me that there was that many papers written on just one small topic.
No, it makes sense, right? Because you got introduced by a teacher, and then all of a sudden you looked into it and thought it might be a small area, and it looks like there's a lot of work being done on it. So that's that makes sense. Thank you. What about you, Dhruva?
One big thing was that I realized how many applications computer science has in other sciences and like other just subjects as well. I thought it was mainly just in chemistry, biology, and physics, but through my project, I realized even finance as well, like every subject really has a need for computer science and what machine learning can do.
Yeah, absolutely. Definitely moving that way for sure. What about you, Antonio? Thanks, Dhruva.
Yeah, you asked me what surprised me about my research. Sorry.
Yeah, what was the most challenging or surprising about doing the work?
Well, part of my project was actually writing a research paper, and my mentor really helped me with that. So going into that, I thought research papers were this big scary thing that you only do in graduate school. But through Polygens, I learned that it's actually quite a doable thing, and if you're really passionate about your work, that it's definitely something that almost anyone can do.
Yeah. And I love that you word the word passion. That's really what Polygens is all about. So that's great. Great usage there, Antonio. Thank you. We're going to record that. And Tejas, what about you?
So since I did not have much experience with neural networks, I first thought like if you can just plug in any data in a neural network, the results will be nice. Because also I'd also done a summer program where I'd use neural networks for medical imaging, and like there was already data that was given to us. So I just had to create a neural network, plug in the data, and it worked. But I realized when I was finding my own research question, like especially in baseball, it's not as simple. It's not just black and white. The neural network works or not. There's a lot of gray area because like just plugging in data doesn't necessarily work. Like I also had to change my question multiple times because I realized that the neural networks, they were not suited to my previous questions. And then I chose this one because I realized there was a feature analysis aspect to it, which I thought would be very practical. So that was what I learned. It was very surprising that how difficult it is to find the right question basically find the right question.
Yeah, I think that was even the question that Shannon had asked you, right? Would you try something different the next time, just based on what you had mentioned in your research? So that's great. Thank you. And then Mihir, what about you?
Sure. So for me, it was just finding out just how much diversity and competition there was in the industry before Moore's Law, and how that's sort of starting to pick up now again. And just from my other peers presenting here, I see that there's so much going on in these industries like AI, machine learning, neural networks, and how just the computing industry, it's been shifting to adopt to their needs as well.
Yeah. It's kind of what Dhruva said, right there. It's used everywhere. It's everybody who did a different subject and literally could take the machine learning and computer science down the rabbit hole on any of these projects. So very, very well done, all of you. So happy to be a part of it and listen to these presentations. You all did a wonderful, wonderful job. For now, it's Saturday for you all, and feel free to enjoy the rest of the panel discussions that we have coming up. And then other than that, enjoy your weekend. And thank you so much for taking the time to share with us all your work.
Thank you.
Thank you.
Thank you so much. Bye.
Thank you.